So in this video, I wanted to cover the specific heat capacity of solids as part of the series on condensed matter physics, specifically solid state physics. Um, so in this video, I want to talk about the Einstein Solid calculation for the heat capacity. Um, and in future videos, I'm going to talk about the Debye theory of solids and go from there. Um, to start with some background, uh, some, some background. So, from uh, basic thermodynamics, we know that the heat capacity of a solid is at constant volume is 3 over 2 kb. And this is per atom of an ideal gas. Heat capacity of an ideal gas, not solid. Uh, Ideal gas at constant volume. And we can derive this using some thermodynamics. So if we consider a piston, um, so imagine this piston is just compressing that way, and this has a length L and an area of A. So area A. So now we want to imagine compressing an ideal gas with this piston and try to derive the heat capacity 3 over 2 kb from this little setup that we have over here. So the ideal gas law, PV equals kBT. And from here, we can imagine as we're compressing the piston, we have the ideal gas molecules bouncing off the walls, hitting the piston, and doing all sorts of things and colliding with the surroundings. So some has some velocity, and this velocity has a Vx component. And from here, we can say pressure is just force per unit area. So force over area. And we know that force is just equal to the change in momentum over the change in time. And this is just equal to so if we consider one trip of the molecule hitting the wall, bouncing back, its change in momentum, if its initial velocity is Vx after the collision, we're assuming it's the collisions are elastic, so the velocities just get swapped. So mvx, change in momentum, divided by the change in time. And this gives us force equal to negative 2 positive 2m Vx over delta t. Now from here, we just have to say that the distance traveled is just a length L, and so, sorry, 2L, right? So we want the molecule to start here, go to the wall, bounce back, and come back to the piston. So that's a distance of 2L. So distance over time equals our velocity, Vx. which is just equal to 2L over a time interval delta t. So this is delta t. From here, we can just plug in the expression for delta t back into the force equation. And we see that 2L over Vx equals delta t. Therefore, the force then becomes 2m Vx over, plug the delta t into the denominator, over 2L. So now this cancels out, and we get our so this would be our force, and if we just divide this over by the area, so we get the area over here, so divide by area on both sides, and we just get our pressure. This is the momentum. Sorry, that was unclear. So with the equation for pressure, we know that pressure equals mvx squared over L times A. Length times the area would just be the volume of the container, so V. From here, we see that for, and if we just multiply over the volume on both sides, we see that P times V, P being pressure, is just equal to mvx squared. And for n particles, of course, we would just have n times the mvx squared. So for n particles, PV equals n vx squared. From here, we can just right, so PV is equal to n times kBt from the ideal gas law. So this is also equal to n kBt. So we can say that for a single particle, so if I divide over by n, this goes away. So for a single particle, mvx squared is just kBt. I'm sorry, you can't see that. So this has to be true from the ideal gas law. If that has to be true, then we can say that, notice how this is just kinetic energy in one dimension. So the x velocity is being squared times the mass. So if we just, half of that would be the kinetic energy. So we can say that, and that's just for the x direction. So per degree of freedom, we have 1/2 kBt of energy. And this is something specific for a more generalized scenario of equipartition theorem, as they call it. So if I go back here, I can say that it's 1/2 kBt. And we see that per degree of freedom, we have kBt over 2 amount of energy. So equals energy. This is per degree of freedom. Because if we considered the velocity in all three directions, then this would just get multiplied by 3. So we can say that E total in 3D is F over 2 kBt. F over 2 kBt. And of course, this is just for one particle. So if we want the total energy of the system for n particles, we just multiply by n. With that being said, we know that we can also call this the internal energy, U internal. So this is the fact that there's 1/2 kBt of energy per degree of freedom. This is a generalized case of the equipartition theorem derived from statistical mechanics. So we can just say a result of equipartition theorem. From here, our initial goal was to find the heat capacity at constant volume. So if we go back a little bit, we can say, a couple more steps and we can get the heat capacity. This is length L. Okay, so from here, we can say that from the first law of thermodynamics, we know that du is just equal to dw plus dq. And at constant volume, we know that work is just 0 because this is p dv. So negative p dv. dv cancels out at constant volume. So we have du equals delta q. And by the definition of heat capacity, which is just change in the change in temperature for the change in heat per change in temperature, is just C dividing over by dt by both sides. We see that du dt is our expression for CV. And from our previous result, we know that U internal is just F over 2 kBt. And in 3 dimensions, it would just be 3 over 2 kBt. So, the dt of our 3 over 2 and kBt, we get 3 over 2 and kb. And of course, this is for n atoms. And if we just divide over by n, we get the result 3 over 2 kb, which is the heat capacity per atom, or per atom of an ideal gas. CV for n particles. Right. So with this general, background and I guess a reminder of thermodynamics, we can proceed further to the more generalized discussion of this video, which is the heat capacity of solids and specifically Einstein's calculation. So let's move on. So now, for many solids, the heat capacity, not at constant volume, just the heat capacity per atom ends up being this an empirical result. C equals 3 kb per atom for many solids. Um, and this is known as the Law of Dulong Petit. Forgive me if I spelt the name wrong, but so this is a result of what's known as the Law of Dulong Petit, which tells us that the heat capacity per atom for many solids at room temperature. So this is an approximation which works extremely well at room temperature. However, it quickly falls off as the temperature starts going down. The Law of Dulong Petit obviously does not hold, and let me just give you an example of a few solids whose heat capacity works really well with the Law of Dulong Petit at room temperature. So some solids, aluminum 2.91, which is the value of, this is the C over kV value. This can also be written in terms of the ideal gas constant, which is C over R, approximately 3. So this is the C over R values for aluminum, for antimony, 3.03, copper 2.94, and gold 3.05. So as you can see, it works quite well at room temperature. At room temperature. However, this drops significantly. The value does not equal 3. It does not equal 3 as the temperatures drop close to absolute zero, and generally away from the room temperature. So at the low temperature limit, this approximation that the Law of Dulong Petit offers actually sort of breaks down. So the remaining parts of this video is addressing the problem and the various solutions that physicists at the time came up with to basically understand why solids have a rapidly decaying heat capacity as temperatures drop much lower than the room temperature. And we start off in some history. Probably erase this. So some history, 1896, Boltzmann Boltzmann constructed a model that accounts for the Law of Dulong Petit quite well, and he was able to assume that the assumptions of Boltzmann's model to align with the Law of Dulong Petit was that each atom um, in the solid is bound to its neighboring atom. I can't spell neighboring. Also, focusing on a single atom, we assume that it's in a harmonic well formed by the interaction with its neighbors. So each atom is in harmonic well with the interaction with its neighbors. However, it still did not work for the low temperature limit. This was just Boltzmann's model. Uh, this was just Boltzmann's assumptions for a solid just so that it can align with the law of Dulong Petit at room temperature. However, this model still did not accurately describe the decay at the low temperature limit. However, now Einstein comes along. Some of you may know who Einstein was. He was a pretty smart man himself. Um, Einstein comes along in 1907, about 10 years or so later. Um, enters the conversation. And the assumptions that he made for his model of a solid was actually, let me tell you the motivation. So he actually did not take this issue lightly. So he actually wanted to figure out why the heat capacity decay happens at low temperatures. So he decided to create his own assumptions for a solid and use some statistical mechanics to see if his model can accurately predict the observed heat capacities at low temperature. So his assumptions were pretty much identical to that of Boltzmann's. However, he said that every atom is in identical harmonic well with neighboring interactions. However, this time it was in a oscillatory potential with so um, bounded to its neighbors with an oscillatory potential um, with of frequency omega, known as um, so every atom was bounded to its neighbor with a potential energy of the form of some sort of spring with some um, frequency known as the omega, known as the Einstein frequency today. Um, and if we, from the, today we know that from the uh, from the quantum harmonic oscillator potential for quantum mechanics, we know that the we know that when we solve the Schrodinger equation with the oscillatory potential known as quantum harmonic oscillator, um, we get the energy eigenstates um, of, let's see if I have it here. All right, we get the energy eigenstates En equals h bar omega n plus 1/2. And this is just um, the nth orbital energy. A little bit of backtracking, perhaps, for the energy eigenstates. So we know that if we have some sort of Hermitian operator, um, so let me erase the Boltzmann assumptions. So if we have some Hermitian operator O hat acting on some wave function state psi, we get lambda. It satisfies the eigenvalue equation, where lambda is known as the eigenvalue, and this is the eigenstate of the Hermitian operator. Okay, so we can think of the operator acting on some sort of vector, and it results in the vector being scaled by an eigenvalue lambda. And of course, it's a vector space, not a vector. So just for simplicity at this moment. And for energy, we know that the Hermitian operator is known as the Hamiltonian. So the equation that we're concerned for, so the eigenvalue equation that we're concerned with in the energy context would just be the Hamiltonian acting on the wave function psi equals En. And now we know that En is the eigenvalue associated with this transformation. However, the En, the eigenvalues, are known as the eigenstates, which give us the specific observable energies of the wave function. So we can't really observe any energy states that's in between the values offered by the E sub n values, which is why they're known as eigenstates. They're the observable values due to the quantum mechanics. And of course, this was before Schrodinger came up with his wave formulation of quantum mechanics. However, this is just something important to know for the, where does this come from? So again, we add some sort of oscillatory potential energy into our Schrodinger equation, solve it, and these are the eigenstates that we get for energy. With that being said, let's okay. So now let's proceed with Einstein's calculation. I'm going to just leave this up here for reference. Okay. So now to proceed with Einstein's calculation in detail, um, we know that, again, let me just write the energy eigenstates for this potential. Um, okay, so we know that the one-dimensional partition function from statistical mechanics is the sum of the Boltzmann factors for each of the microstates, and we have one microstate per energy eigenstate. So we get Z1D equals e to the negative beta times the energy eigenstates, which is h bar omega times n plus 1/2. Okay. Again, this is just the sum of the Boltzmann factor for each of the microstates of our system. And of course, this is just a geometric sum. So this is a geometric sum which converges to e to the negative beta h bar omega over 2 divided by 1 minus e to the h bar omega. Let me move on to that side over there. And this is just our partition function. Just a context, sorry. Beta is just 1 over kb times the temperature. So 1 over the Boltzmann constant times temperature is beta. And now we can rewrite the 1D partition function in terms of hyperbolic trig functions. So Z1D can also be rewritten as 1 over 2 sinh h bar omega over 2 kBt. And this is just a small algebraic exercise you can work out. And now the expectation of the energy is just equal to the negative partial derivative of the log of our 1D partition function, which is, this is equivalent of saying if we do a change of variables using chain rule in terms of temperature, if you want the derivative, it just becomes kb t squared ln over partial t. So this is just our equation from StatMech for the expectation of energy. And if we just apply this equation to our 1D partition function, we see that equals h bar omega over 2 times hyperbolic cotangent of beta h bar omega over 2. And this is just equal to h bar omega times NB. I'll tell you what NB is in just a second. NB evaluated at beta h bar omega plus 1/2. Okay, so NB is actually the Bose occupation function, which is given as NB of x is equal to 1 over e to the x minus 1. And this just tells you the number for any boson, the number of bosons occupied at a certain frequency omega. And that's what this tells us. So basically, NB of beta h bar omega is just the Bose function, the Bose, forget the name for it, the Bose distribution. I believe it's called the Bose-Einstein distribution. Bose-Einstein distribution evaluated at some specific frequency omega. And that tells us the number of bosons that have that specific frequency and the number of bosons occupied at that energy level. And yes, so this sort of wraps up this part of our discussion for energy. And of course, we can take this a step further. Let me just erase this. So we can take this a step further, and we know the equation. Now that we have the expectation of energy over there, we can just simply find the heat capacity by differentiating the expectation with respect to temperature. And when we do that, we just get KB h bar omega squared e to the negative beta h bar omega over e to the beta h bar omega minus 1 squared. And this is just, I skipped some of the derivative exercises over there. This is our equation for heat capacity using the Einstein assumptions that Einstein made, where each atom is bound to its neighbor in some oscillatory potential well with a frequency omega known as the Einstein frequency. And now from here we can quickly see what happens. So now this is just the general heat capacity expression that Einstein came up with. And now we can see, we know that the law of Dulong Petit holds quite well at the high temperature limit, which is the at the room temperature. So if we just try to use a Taylor expansion for the high temperature limit, for this expression, we can say that so e to the x 1 plus x, just for a reminder, we know that c then becomes now kb times beta h bar omega squared. So this is just oh, sorry, this should be a positive, my bad. Yeah, this should be a positive. I was wondering. Okay, yeah, so 1 plus beta h bar omega divided by 1 plus beta h bar omega minus 1. So, sorry. 1 plus beta h bar omega minus 1, so that's just beta h bar omega squared over here. And quickly you see that this cancels, and this cancels because beta is 1 over kBt, so this goes to 0 at the high temperature limit, so C is approximately just kb. Cool. Right. Okay, so let's keep going now, and let's see what happens when we generalize this to 3 dimensions. Okay. I'm going to erase some of this stuff over here. So when we generalize this to 3 dimensions, we see that equals h bar omega. So now you have 3 degrees of freedom, so this just this expression just gets generalized a bit more. Plus ny plus a half plus nz plus a half. And our 3D partition function is just beta. So this is the sum where nx, ny, and then the energy eigenstates for each of the 3 dimensions. Okay. And again, if we going through the exercise where we use the derivative for energy expectation on this all over again, we just see that C equals 3 times the expectation that we got for the 1D case. So it's just 3 kb e to the beta h bar omega over to the beta h bar omega minus 1. Okay, so yes. Now when we do the high temperature, okay, I should point out that you should be a bit confused as to why we only got a kb here when we Taylor expanded this. We should get a 3 kb because the law of Dulong Petit gave us 3 kb. So it's a problem that we're off by a factor of 3. And that's only because this was only our value for the 1-dimensional case. When we do this in 3 dimensions, we get an expression for C, which is very similar to the one we got over here for C, except it's just differing by a factor of 3. So as you can see, if I just Taylor expand this for the high temperature limit and do what I did over there a second time, I should get C is approximately 3 kb. And that's a very good result because now we see that Einstein's model is agreeing with the law of Dulong Petit at the high temperature limit with 3 kb. Great. It would have been a problem if it didn't. All right, so we're almost done here. Let's just move on to the final remarks. So I just want to show you how Einstein's model actually works at the low temperature limit. Um, and if we actually plot, um, if we plot, that's one, if we plot kBt over h bar omega versus c over 3kb, based on Einstein's model, we see that um, something like this. So as you can see, at the high temperature limit, as T goes much, much larger than the oscillation Einstein frequency, we see that C asymptotically approaches the 3 kb value, which is very good. And if we look at the low temperature limit, the Einstein model actually predicts a exponential drop here in the heat capacity and asymptotically approaching zero at absolute zero. And this is, again, just, we already did this with the Taylor expansion and showed it's 3 kb. So as a plot, this is how it looks. And you might be wondering, what's actually happening? Why is the heat capacity actually dropping off to zero? This is because if you physically think about it, the heat capacity tells us that what the change in temperature is, or how much heat can we extract from the system for every amount of temperature that we change. As we get closer and closer to absolute zero temperatures, it becomes more and more difficult to remove heat out of the system, which is why the heat capacity gets to zero. It's just telling us that no matter how much we change well, you can't really go past absolute zero, right? So your delta T is your delta T is sort of frozen at around zero, and you basically cannot extract any heat out of the system, or it gets extremely, extremely difficult to remove heat from the system as you get closer and closer to absolute zero. And this is just an illustration of that phenomenon. I will say that for most materials, the Einstein frequency omega is actually low compared to the room temperature. Therefore, the law of Dulong Petit holds well, right? So if omega is extremely low compared to the room temperature, then we know that we're higher on the right towards this graph. So the law of Dulong Petit value is what we approach. However, in materials like diamond with extremely high omega values, we see that the heat capacity actually sort of drops, right? So if we have high omega at room temperature, we see that the value actually still deviates from the law of Dulong Petit. So basically, high omega, same temperature, we still move off to the left. So the diamond actually is an exception where we get a value that deviates from the law of Dulong Petit even at the room temperature limit. And that just has to do with the oscillatory frequency omega. And basically, the carbon atoms are extremely light, and diamond is very strong, leading to a higher oscillation frequency. And the high oscillation frequency not only lowers the heat capacity, but also explains the diamond's hardness, how tough it is. So the Einstein model was groundbreaking because it basically explained the temperature dependence of heat capacity before the formal development of quantum mechanics. So even the um, so the Einstein model not only explains the exception for diamond, which tells us that due to this high oscillatory frequency, we still deviate from the law of Dulong Petit at room temperatures, but it also perfectly predicts the law of Dulong Petit for other materials at the high temperature limit, and also predicts the exponential drop off to zero at the low temperature limit, which makes perfect sense with um, physically. So we'll call it there, and in the next video we will talk about some other models of solids.